Hey guys, hope everybody's doing okay. What we're going to do today is continue with our unit on kinetics, and we're going to talk about something called integrated rate laws. Integrated rate laws is one of the longer lessons of this unit, but it's also one of the last lessons of this unit, and it's very heavily math-based. So let's go ahead and figure out what this is and see what it's all about. Sometimes if we have a chemical reaction, like in this case we have some reaction with N2O5 in it, and we want to figure out how much N2O5 is going to be left after a certain amount of time, maybe 5 seconds or 5 minutes. Now what we can do is actually take our rate laws, we could apply some calculus to those, and we could come up with something called an integrated rate law. An integrated rate law is going to tell us how much reactant is left after a certain point of time in our chemical reaction. So we're going to find the integral of these, and I'm just going to show you what the end result is. We're not actually going to go through all the calculus right here, but we're going to integrate the rate law with respect to time, because we want to find out how much reactant is left after a certain amount of time. And then that's going to give us some different equations. So the equation that we're going to end up using, the integrated rate laws, are going to be dependent on what order the reaction is. So is it a 0, first, or second order reaction? That's going to give us the 0, first, or second order integrated rate law. Let's start out with the 0 order integrated rate law, and to figure all this out, we need to start with just the regular rate law for a 0 order reaction. So a 0 order reaction, if you remember, does not involve a concentration of any other substance. It is independent of the concentration of the items that you have. So the rate is simply equal to K, your rate constant. What we can do is substitute the definition of rate into the word rate. So rate is a change in concentration, which is A sub 0 minus A sub F, I guess, final concentration, over delta T, our change in time. So here's where we get our time term. Okay, so we apply some calculus to this, we integrate this with respect to time, and what we're going to end up with is an integrated rate law that looks like this. Okay, this is the integrated rate law for 0 order reactions. You may need to add this to your note sheet because it may start at first order instead of 0 order, so please be aware of that. Add a little section here for a 0 order integrated rate law. So what do all these symbols stand for? Obviously these are brackets, and that is concentration. So it's the concentration of your substance A at time t. Okay, so maybe after 5 seconds, that's the concentration, or after 5 minutes, that's your concentration. A sub 0 is your initial concentration. Okay, we already know that K is our rate constant, and T is our actual time. Okay, so A sub T, if the time is 5 seconds, A sub T is our concentration at that 5-second mark. Okay, so what we can do is if we're given some information about the chemical reaction that we have, we can plug it into this integrated rate law if it's a 0 order reaction, and we can solve for one of these variables. The one that we want to solve for here. It could be concentration, it could be initial concentration, it could be your time. We could solve for a variety of different things. Okay, so it's our 0 order integrated rate law. And there's a form of this on your formula sheet, the AP Chem College Board version of it that they give you. I'll show you that later and talk about that. So the next one is first order integrated rate law. We'll spend a little bit more time on this one. So our regular rate law for a first order reaction is rate equals K times the concentration of A. So we're going to do the same thing. Let's substitute the definition of rate into that, and we get our change in concentration over time equals K times the concentration of A. Let's take the integral with respect to time, and our integrated rate law for a first order reaction is going to look like this. We have the natural log of A sub T minus the natural log of A sub 0 equals negative KT. So again, what do the symbols stand for? It's the same as before. A sub T is your concentration at time T. A sub 0 is your initial concentration, and then your rate constant, and T is your time. Okay, so that's our integrated rate law for the first order reaction, and this is the version of it that is on your AP College Board equation sheet. So let's go through a couple examples and see how we apply this. So for the rate equals K times N2O5, determine what concentration of N2O5 is left after 4 minutes of an initial 0.16 molar solution if the rate constant K equals 0.35 per minute. So first thing I need to figure out here is if I'm using my integrated rate laws, what is the order of my chemical reaction? Well, it's giving me my rate law right here. My rate is equal to K times N2O5. It definitely looks like a first order chemical reaction, so I'm going to use my first order integrated rate law. Let's go ahead and label everything that we have here. We have 4 minutes, so that is time t. We have an initial concentration, so that's going to be A sub 0. And we have our rate constant K. Okay, so we have that. What don't we have here? Looks like we do not have the A sub t. All right, so A sub t is our question mark. All right, so what we want to do is plug all this into our integrated rate law, and we want to solve for A sub t. So let's go ahead and rearrange the equation first. I'm going to move my natural log of A sub 0 to the other side. So I'm going to add it to both sides. Okay. Oops, natural log. And then I'm going to clean this up a little bit. I'm going to get my natural log of A sub t equals, I'm going to plug my numbers in now. I have negative K, and my K was 0.35 per minute times t, which was 4 minutes. It's very important that you look at your unit on K and look at your unit on time and make sure they match. So both of those are a unit of minutes there, or per minute and minute, so that's going to cancel that as good. Plus natural log of A sub 0, which was 0.160 molar. Okay, so what I'm going to do is I could plug all this into my calculator, which is what I would do. Okay, so type in negative 0.35 times 4 plus natural log of 0.16, and you're going to get some number for that. And then you want to undo your natural log here. So let's go ahead and plug that in, and then you're going to get natural log of A sub t equals that number. What we want to do then is undo our natural log. So you're going to raise all of this. You're going to raise e to all of this. We did this with our in our thermodynamics unit. Okay, so we're going to have e to that number. All right, and that's going to give us A sub t. If you plug it into your calculator the right way, what you should end up with is a concentration at point t. So A sub t is equal to 0.39 molar. Okay, that makes sense because you're going to have the per minute and minute cancel out here, and the unit you're left with is molar, which is good because you want your concentration, right? And the concentration is in molarity. So that takes care of how you do that. So you could plug all that in and then take e to all of that. Just make sure your signs are correct, and you should end up with, again, 0.039. If you're not getting that, we have to double check our calculator and make sure it's coming out the correct way. Next one. It says, what's the concentration after 12 minutes of an initial 0.5 molar solution? So we're assuming that this is the same chemical equation and that it's first order. So we're going to go through and solve this one. So our time is 12 minutes. That is t right there. Okay. Initial concentration, so that is A sub 0. We already have K. It's the same as our last example. All right, so that is 0.35 per minute. And what I'm trying to solve for here is, again, A sub t. All right, so what we want to do is, same thing, reorganize this, and you're going to get natural log of A sub t equals negative kt plus natural log of A sub 0. All right, you're going to want to plug in everything and then solve it. So we're going to get negative 0.35 per minute times t, 12 minutes, plus natural log of 0.50 molar. All right, go ahead and solve that. That'll give you some number. Then you take e to that number, and that's going to give you the concentration of A sub t. And after all is said and done, what we should end up with for an answer here is 0.0075 molar for the concentration after 12 minutes. Okay, so that is solving for A sub t, rearranging that equation. Let's take a look at a third example using this one. And we're going to have the question asking us, how much time does it take for the concentration to drop from 0.16 molar to 0.10 molar? So a couple things are consistent here. Our K, the same reaction, is 0.35 per minute. Our time is what we don't know. And in this case, we have to be really careful here. It says the concentration is going to drop from something to something else. So that 0.160 molar, that is our A sub 0. And the 0.100 molar, that is our A sub T. All right? So what we want to do is the integrated rate law for the first order reaction again. Okay? And we're going to go ahead and fill that in. So that is the natural log of A sub T minus natural log of A sub 0 equals negative KT. Let's solve for temperature, so divide both sides by negative K. And you end up with natural log of A sub T minus natural log A sub 0 over negative K is your time temperature. Okay, so what you want to do is make sure you use your calculator properly. So the numerator here, make sure you figure that out first. So make sure you type that in with parentheses around it, or else you're going to be all messed up here. You're going to have an order of operations issue. And plug it all in. So your A sub T is your 0.100 molar, your A sub 0 is your 0.160 molar, and your K is 0.35 per minute. And you should end up with your time. Okay, if you end up doing that correctly, you should get an answer of 1.3 minutes, and that popped up a little bit earlier than I wanted to, but hopefully you're using your calculator correctly and you're getting that answer. All right, so there's my first order integrated rate law right there. Last one here leads us into something called half-life. So for a first order reaction with a rate constant of 0.12 per minute, how much time would it take for the concentration to get cut in half? So it's saying it's a first order reaction, and the rate constant is new here, so it's a different chemical reaction, and that rate constant is 0.12 per minute. So how much time would it take for the concentration to get cut in half? Now it's not giving us a concentration here, but that's fine. What we can do is say that my initial concentration, let's just say my A sub 0 is 1 molar, okay? And I want to get cut in half, so my A sub T is 1/2. Let's just, it's 0.5, right? Let's just make that a little bit nicer. So 0.5 molar. All right? So I have K. I have my initial concentration. I'm just saying it's 1. My final concentration, I'm saying it's 0.5. I want to solve for T. So we just did that on the last problem. So let's rearrange this and solve for time. And we're going to get, so again, natural log of A sub T minus natural log of A sub 0 over negative K equals my time. Let's plug everything in. Natural log of A sub T is 0.5 minus natural log of 1 over negative 0.12 per minute equals time. Plug in your calculator and you're going to end up with a time here of 5.8 minutes. All right, so your time is going to be 5.8 minutes. What I want to do here is show you a little bit of a shortcut. So this is definitely asking you basically for the half-life here. The definition of half-life is how long it takes for half of a substance to decay. All right, we learned about that in Chem 1. If I take my integrated rate law for a first order reaction and I just reorganize it, you actually end up with this version of it. Okay, it's just how natural logs work. You could simplify natural log of A sub T minus natural log of A sub 0 as simply the natural log of A sub 0 over the natural log of, or really the natural log of A sub 0 over A equals KT, a positive KT. All I did was reorganize this using some algebra into this version here on the left. I just want to prove a point to you guys. What you can do then is recognize that, it's cut off on here, but your A sub T is always half of A sub 0. Okay? So whatever your A sub 0 is, take half of it and you have A sub T. So let's substitute that in to this equation I have on the left. All right? So natural log of A sub 0 over, and instead of saying the concentration of A sub T, I'm saying 1/2 A sub 0, because that's exactly what it is. We figured that out over here. Okay? Simplify. Look what happens. Your A sub 0s cancel out. What you're left with is natural log of 1 over 1/2 equals KT. Simplify that further, you get natural log of 2 equals K times T 1/2. And I just made T 1/2 as the half-life. That's the time. Okay? So this is really interesting because all first order reactions are going to work the same way in terms of half-life. All right. Try a couple different numbers. Like I could have made this, if I wanted to, instead of 1 and 0.5, I could have said 20 molar to start with, and then 10 molar, because it's still cutting my concentration in half. And in my equation here, if I did natural log of 10 minus natural log of 20, I'm still going to get 5.8 minutes as my answer. What you see here on the left, when I simplified this and reorganized it, is you're always going to get a natural log of 2. Okay, so it's always natural log of 2 equals KT. That's always what you're going to have for half-life reactions first order equations. The College Board equation sheet has this on there for you. It's the only half-life equation you're going to have to worry about, and they actually simplified it a little bit more for you, and you're going to end up with a reorganization of this, and you're going to end up with T1 half equals, the natural log of 2 is 0.693. You're going to get 0.693 over K. This is on the College Board equation sheet. Okay, so that natural log of 2 is a constant, 0.693. Divide that by K, which is in this case 0.12, and you'll get that time. So try it. Type in 0.693 over 0.12, and you're going to end up with 5.8 minutes for your half-life. Okay, so it's really cool how that works out. So use that to your advantage. If you forget that, though, you could just use the integrated rate law for first order, and you're still going to get the right answer. But it could save you a lot of time recognizing that you could use the first order half-life equation and just simply do 0.693 over K, and you're done. No need to worry about natural logs and maybe making a silly calculator mistake. All right, so it takes care of that. Okay, so here's a slide that's going to summarize half-life for first order reactions. So use the integrated rate law formula to determine the half-life formula. So again, I simplified that for you on the previous slide. So we have natural log of 2 equals KT. Simplify that natural log of 2 and reorganize the equation, and you get T1 half, or your half-life time, equals 0.693 over K, which again is what is on the AP College Board equation sheet. So for first order reactions, half-life does not depend on concentration. This is really important. Here's your half-life, T1 half, for first order reactions. And notice that it only depends on your 0.693, that's a constant number, divided by K, your rate constant. It does not have a concentration term in here at all. So it's really important to know for first order reactions, half-life does not depend on concentration. So something to highlight or make sure you pay particular attention to. Half-life is the same regardless of starting amount. This is also really important. This is different from second order half-life problems. So the half-life is the same regardless of starting amount. So you could start with 1 molar, 2 molar, 10 molar, 0.5 molar. The half-life will remain consistent. This is applicable to radioactive decay since they are first order reactions. All radioactive decay is first order, and there was a question or two on the College Board exam a few years ago about this, so it's important that we recognize this and we know this. So alpha, beta, gamma, we did those different decay equations earlier in like really in honors chem. So that is what we're talking about here in terms of half-life and nuclear decay. Common example is carbon-14. Carbon-14 always takes 5,730 years for half of it to decay. And I remember in honors chem we did some practice problems with that. So if you have 5 grams of carbon-14 in 5,730 years, you will have half of that. In another 5,730 years, you'll have half of that. And it'll keep taking 5,730 years for half of it to decay. All right? So go from 10 grams down to 5, takes that much time. 5 down to 2.5, takes that much time. You can keep going from there. Okay? One more half-life problem for first order, and this is going to be solved in a similar way to some of the honors ones that we did last year or 2 years ago. It says a certain first order reaction has a half-life of 20 minutes. Calculate the rate constant. All right, so let's go ahead and figure that out. We want to figure out K here. So let's use our simplified formula for this, which is T1 half equals 0.693 over K. So it says it's first order. Use your first order half-life equation, and it says the half-life is 20 minutes. So we're going to have 20.0 minutes equals 0.693 over K. Simplify it, use some algebra here. So we have K times 20.0 minutes equals 0.693. Solve for K. And you get K equals 0.693 over 20, and there's no unit in the denominator. There is a unit, and there's no unit in the numerator, I should say. There is a unit in the denominator, which is in minutes. So your answer is going to be whatever the number is per minute. Okay, so we're going to look at this in a few minutes here. The rate constant for first order reactions is always going to be per minute or per second. Okay, so that is important to know. If you type it into your calculator the right way, you're going to get a rate constant of 0.0347 per minute. All right, next one. Our first order reaction has a half-life of 20 minutes. K is 0.0347 per minute, just like the last problem. How long will it take for the material to reach 1/4 of its initial value? So let's go ahead and figure this out. Now we know it's first order reaction, so we have a couple options here. We can use the first order integrated rate law, and you have your a sub 0, you could just say is 1, just make your life easy. And then you want to know how long it's going to take for the material to reach 1/4 of its initial value. So you want your a sub t, and you don't know what the time is, you're trying to figure it out. Your a sub t is 0.25 molar. It's 1/4 of the initial value. Okay? What you could have recognized here is, since it's first order and the half-life is 20 minutes, if you start with 1 molar and it decays down to 0.5 molar, that is going to take you 20 minutes. If you want 0.5 molar then to decay into 0.25 molar, that's clearly half, right? 0.5 divided by 2 is 0.25. That's going to take another 20 minutes. So your answer here is 40.0 minutes of time. That's the easiest way to do it. But you could take your integrated rate law, plug in 1 molar for a sub 0, 0.25 molar for a sub t. You have the K value of 0.0347 per minute. The only unknown you have here is t, with the time that's going to take. So you could do it that way, and you're going to get 40 minutes as well for your answer. So I think this is easier if you could pull it off this way. The other way, though, is also valid and definitely something you can do. Second order integrated rate law we'll do very quickly here. So here's our rate law, our regular rate law for second order reactions. It's rate equals K times A squared. If I substitute in change in concentration over change in time for rate, integrate with respect to time, I'm going to get a second order integrated rate law of 1 over a sub t minus 1 over a sub 0 equals positive kt. So that's different than the other two that we looked at. The other two had negative kt on the right-hand side of that equal sign. This time we have a positive kt over there. You can find the half-life formula for this, for second order reactions, and that's T1/2 equals 1 over K times A sub 0. The important thing to recognize here is that for the half-life formula for second order reactions, there is an initial concentration here. So the initial concentration is making an impact on that half-life, whereas with the one that we looked at earlier with first order integrated rate law and first order half-life, it was just 0.693 over K. There was no initial concentration there. So important note to make here is that the initial concentration has an impact on the half-life for second order reactions. It's one of the big differences between the two of them. This is not on your formula sheet for the College Board. So if you ever needed to use it, you would be given that formula. Odds are you're really not going to have to use it, but you still have to know the difference between first and second order half-life. So that wraps up our integrated rate laws for 0, first, and second order reactions. But what I want to look at now is look at some patterns we can find. Let's focus on units a little bit, and then we're going to look at some graphical interpretations of these, which is really, really important to understand. So units make a big comeback here again in this unit, because you could tell a lot about your chemical reaction and what kind it is based on what the units are on your rate constant. Let's take a look at the first bullet point here. It says the units on K, your rate constant, for all zero order reactions are the same. So if you take a zero order rate law, which is simply rate equals K, figure out what your units are going to be on K. Well, you know rate. Rate is always change in concentration over change in time. So the rate is always going to be molarity per second. So substitute molarity per second in for rate for all of these and solve for K. Well, in this case, rate equals K, so molar per second equals K. This is for a zero order, okay? Zero order is always going to have molar per second as the unit on K, always and forever, all right? Because rate is molar per second and rate is equal to K. Let's look at a first order reaction. First order, we'll do here. Okay, first order reaction is rate equals K times the concentration of A to the first, right? So substitute in what we know. Rate is molar per second equals K times, and the concentration of A, the unit is molarity. Okay, divide both sides by molarity, and what you end up with is 1 over seconds equals K. Okay, so the unit on K for first order reactions is always going to be 1 over seconds or 1 over minutes. It's 1 over your unit of time. Okay, let's do the second order. Second order is rate equals K times A squared. Okay, even if it's rate equals K times A times B, you still have the same unit on A and B. It's just molarity. So let's do some substitutions again. Rate is molar per second equals K times molar squared. Divide both sides by molar squared. One of them cancels out. Okay, and what you end up with is 1 over molar times seconds equals K. All right, so for second order reactions, your rate constant is always going to have a unit of 1 over molar times second. So if all you're given is a rate constant, and you know the rate constant is, for example, 1 over seconds, you know it's a first order reaction. If you see your rate constant as 1 over molar times second, you know it's a second order reaction. We could just keep applying this and look at third, even though they're very rare, third order reactions have a rate law of rate equals K times A to the third, and that's going to be molar per second equals K times molar cubed, and then divide both sides by molar cubed. Okay, simplifies, you get 1 over molar squared times seconds equals K. This is always your unit on second order reactions, okay, for K, for your rate constant, 1 over molar squared times second. So you see the pattern here. Molarity ended up at the top for zero order. It canceled out for first order. It moved to the denominator for second order. And then we have now molar squared in the denominator for third order. Okay, guys? So important to know that and to see those patterns. Here's a little summary of that for you on this slide, so you can make sure you have this information copied down somewhere and you have that available to you. The units for K will change depending on the overall reaction order. We just talked about that. So here it just has 0 first and second because third order is very rare. So you can see what I had here, molar per second, 1 per second, and 1 over molar times seconds. Here is just a simplified version of that without having fractions. Importantly, units for rate never change. Rate is always molar per second. So see how that is consistent throughout. Okay, good to know what the units are on a lot of these things because it comes into play throughout the whole unit that we're studying here. So, to wrap all this up, we could determine the reaction order 3 main ways. So these 3 ways are in your note sheet, and we've done most of them already. So let's take a look at what these are. First one of the very first lessons of the unit, we could perform trials and change the concentration of the reactants to see what effect it has on the rate. So if you have a grid like this, you can take a look at everything that you have here and figure out what is the rate with respect to NO, NO2, and O2, and then put it all together to determine your rate law. So for example, it looks like I kept my NO2 consistent here, my O2 consistent here, I doubled my NO, I doubled my rate, so it looks like that is first order with respect to NO. Alright, so you would go through and then do the same thing. Find the order with respect to NO2, find the order with respect to O2, and then see what you end up with, add up all your exponents, that gives you reaction order. Alright, so that's number 1. Number 2, you can analyze the half-life. So this is important. Let's take a look at some of these graphs. If the reaction is first order, the initial concentrations don't matter. We already talked about that. The half-life is constant with a constant temperature. So please take note of that here. Half-life is constant with constant temperature. Sometimes you're just given a graph and you have to figure this out. So if I gave you this graph and I said, tell me if this is a first or second order chemical reaction, you want to analyze the half-life. So it looks like we are starting here at 0.2 molar, and half of that would be 0.1 molar. How long did that take? So here I am. Looks like it took about 7 seconds. So 7 seconds for that to happen. Let's go from 0.1 to 0.05. So that's my next half-life, right? Time it takes for half of my sample to decay. I go from 0.1 molar to 0.05 molar, and it looks like I'm at T14. So it looks like that took another 7 seconds. And then from 0.05 to 0.025, it looks like I'm about here. And that took another 7 seconds because I'm at, we're doing it in the wrong spot. Here we are. We're at 21 seconds. Okay? So it took another 7 seconds. So I'm a consistent half-life. So the half-life here is consistent, so I know this is first order. Definitely need to know that. Second order is different. The second order graph is going to look like this. So your first half-life looks like it took, let's see, 10, 8, 6, so like 5 seconds. Looks like it took about 5 seconds for that to happen. Or 50 seconds, I should say, because we're going by hundreds here at the bottom. And then look how long it took for the second half-life to occur. We're here. Okay, third half-life, we are here-ish. Okay, so first half-life took about 50 seconds. Second half-life definitely took more time. Third half-life definitely took more time. I don't even really care what the time is. I see it's substantially more though. So that's what a second order half-life graph is going to look like. All right, so first order is consistent. It doesn't matter what your concentration is. The half-life is the same for every time it goes through a half-life. Second order, the initial concentration does matter. And we talked about that already earlier. So the initial concentration here was 0.2 molar, and it took a certain amount of time to get down to 0.1 molar. Now, to go from 0.1 molar to 0.05 molar, here's my new initial concentration, and here's my new final concentration. So the concentration is making an impact here, because if you remember, your second order half-life equation was T1 half equals 1 over K A sub 0. Okay, so that was included. The initial concentration was included in your half-life equation for second order. Okay, but again, you're not going to have to really memorize that unless I tell you to use it, and I would just give it to you. All right, it's not on the College Board equation sheet. That is way number 2 to figure out reaction order. Last one is the conclusion to this lesson, which is very important because you're going to be doing some of this in your iodine clock reaction lab. You're going to have to analyze these. It's applying the concentration and time graphically. Let's take a look at what the graphs look like for 0, first, and second order reactions. So, 0 order reactions, we have our integrated rate law, and all I did was reorganize it. Okay, so I did this on purpose because I initially had a sub t minus a sub 0 equals negative kt. All I did was move the a sub 0 over here to the right-hand side of the equal sign, so I could make my equation in the form of a certain format here. So what's the graph of concentration versus time look like for 0 order reactions? Concentration versus time looks like this, and what we end up with is a straight line, and that's very important. The general formula for a straight line is y equals mx plus b. So if I take my integrated rate law for 0 order reactions and I reorganize it into that y equals mx plus b format, that's what I end up with here. So look, y equals mx plus b. All right, my y is my concentration, it's on my y-axis. My slope is actually my rate constant, and you can see that it's going down, so it's a negative value, so it's negative k, times t, which is time. Time is on my x-axis, see how nice this is working out for us, and then we have plus b, which is our y-intercept, which is our initial concentration. Look at that. It's where we started, and the reaction proceeded as the time goes on. So it's really nice how this works out. You could figure out a lot of information based off of that line. So the plot of concentration versus time is linear. What we want to do here is figure out what could we graph to make a linear line, and that's going to tell us some information about what we have. So slope is negative k for 0 order reactions in the y equals mx plus b format. when we do concentration versus time. That's our linear line there. So that's important to understand. A zero order reaction will give you a linear line when you do concentration versus time. That's different for every other order reaction that we have. So here's a first order reaction. I'm taking my first order integrated rate law, I'm reorganizing that, so I'm going to end up with natural log of a sub t equals negative kt plus natural log of a sub 0. What does the graph of concentration versus time look like? It's actually going to look like this. So concentration versus time is not linear for a first order reaction. So we can't use y equals mx plus b. What we can do, though, is graph the natural log versus time. And that's why in your first order integrated rate law, we have the natural log in here. Okay? So a natural log of concentration versus time graph will be linear. First order reactions are going to show us that. So if you take the plot of natural log versus time, that's linear for first order, and our slope becomes negative k. So again, the same thing. Natural log of a sub t is my y-axis, m is my slope, t is time on my x-axis, plus the natural log of a sub 0, that's my initial concentration. Natural log of that is where I'm starting my chemical reaction, and I'm proceeding in this direction. Okay? So that's something to understand and make sure we know for first order reactions. You're graphing natural log of concentration versus time. That's going to give you the linear graph. Last one, second order. I take my integrated rate law and I reorganize it like I have up here on the screen. And if you look at what you're graphing here, concentration versus time is not going to give you a linear line. Natural log of concentration versus time, which is the graph on the left, is not giving you a linear line. But if you do graph 1 over the concentration versus time, look what you get. You actually get a linear line there. So look at what we end up with here. Plot of 1 over a, where 1 over concentration versus time is linear. That's really important. It's what we want to look at for second order reactions. So I reorganize my integrated rate law, and I end up with my y equals mx plus b format. And again, 1 over concentration is my y-axis. Slope is actually positive k. All right, that's something to make sure we understand here because my slope is a positive line. So slope is positive k. My x-axis is still time, so that's where I get my time and my x from, plus b. B is my y-intercept right here. It is 1 over my initial concentration is what I have, so it works out perfectly. So what we want to understand here is what do you get in terms of a linear graph for 0, first, and second order. So if you graph concentration versus time, if you graph natural log of concentration versus time, and if you graph 1 over concentration versus time, one of them will be linear. The one that's linear gives you the order of reaction that you have. Okay, so what you guys are going to need to do between now and next time I see you is to create a spreadsheet. You could use your graphing calculator too, but I would just go into Google Sheets or Excel or even Graphical Analysis. I'm going to show you what this should look like in a minute. You want to make a spreadsheet where you have concentration versus time, natural log of concentration versus time, and 1 over concentration versus time. And you want to create 3 graphs on your spreadsheet. So then you plug in your data, and then the graphs are going to be made for you already, and you can see what order reaction you're going to have. This is going to help you determine a reaction order from looking at your graphs. It's going to save you a lot of time. So let me go ahead and show you what mine looks like, and then we'll wrap up the lesson with some more information. Okay guys, here's mine that I made. So you want to use Google Sheets or Excel or Graphical Analysis and mimic mine, I guess, and do that on your computer. So all I did was make a time column, concentration column, 1 over concentration column, and natural log of concentration column. And then you could even use my data if you want to. I just picked some data from somewhere in your packet. I just have my times in there. I typed in my concentration, and then what I did in my cells here was I did not actually do all the calculations myself. I taught you guys how to use formulas in Google Sheets before. So use formulas here to do this. Hit equals, and then I did 1 over, and I clicked on cell B2. So I want to take the inverse of my concentration. Okay, so I did equals 1 over B2, and then I just did that for all of them. So the next one's 1 over B3, 1 over B4, blah, blah, blah. Okay, so when I type my numbers in here on the left, these concentrations, or this column here, the 1 over concentration, is figured out for me. And then here I did the same thing. I did equals natural log of concentration. Okay, and then filled it in. So I type in my concentrations. Literally all I'm typing in are these numbers here and my times here, and then these numbers are filled in for me. You can see that as you look on the screen for my formulas there. Natural log of B4, B5, B6, B7, B8, because that's how much data I have. And then what I want to do is insert 3 graphs. I'm going to do a graph of concentration versus time. So I just highlight my concentration versus time, make sure concentration is on the Y, time's on the X, and then it's going to plot my data for me. I want to make sure I insert a equation. It's also good to insert your correlation or R-squared value. That tells you how linear your data is. So I type in my information, it does the graph for me. I make one for first order and second order, and I have them all on the same screen. So as soon as I change my times and my concentrations, these graphs are made for me, okay? So again, insert your line of best fit with the equation and R-squared value. So if you look at the data I have on the screen, and you could use mine as an example and you make yours, use my times, use my concentrations, get your graphs, look what you end up with. You end up with an R-squared value of 0.8635. Definitely not linear, it's very curved, you can see that. My first order graph, first order is with natural log of concentration versus time. My R-squared is 0.9945. Well, that's pretty good. Looks pretty linear to me. And then my second order graph is 1 over concentration versus time. And you can see that it is pretty curved here as well. My R-squared is 0.9418, so it's not that good. I picked one as the most linear. In this case, it is 0.9945 for my R-squared value. The linear graph is the natural log of concentration versus time, and that is going to be my first order reaction. So the data here that I'm given is going to give me a first order chemical reaction, and then I could apply my first order integrated rate law and answer questions about this data, knowing that it is first order. If I plug all this data in and my zero order ends up being linear, it's a zero order reaction. If it's second order and my 1 over concentration versus time is linear, then of course it's second order reaction. I use my second order integrated rate law and go from there. Okay, so let's go ahead and wrap up the lesson here, and then we'll take it from there. Okay guys, let's wrap all this up here and look at a rate law graphical review video, and it's going to go through the 0, first, and second order integrated rate laws and show you what those graphs should look like and what we're looking for in terms of how the data will become linear and what that tells us about that data and what order of reaction we have. Take a look at this, then we'll go from there.
Let's explore the differences between the graphical behavior of different reaction orders. In a zero-order reaction, the concentration decreases in a straight-line fashion as time progresses. The rate constant, K, can be determined from the slope of the line. In a first-order reaction, the concentration does not decrease in a straight-line fashion as time progresses. The graph of concentration versus time is a curve. If the concentration data is graphed as the natural log of the concentration versus time, the result is a straight line. The rate constant, K, can be determined from the slope of the line. In a second-order reaction, the concentration does not decrease in a straight-line fashion as time progresses. The graph of concentration versus time is a curve. For a second-order reaction, the graph of the natural log of concentration versus time will also be a curve. If the concentration data is graphed as the reciprocal of the concentration versus time, the result is a straight line. The rate constant, K, can be determined from the slope of the line.
Okay. Again, concluding our summary here of the rate laws, you could see I've highlighted here, this is from your textbook, the plot needed to give a straight line for zero order is concentration versus time, first order is natural log of concentration versus time, and second order is 1 over the concentration versus time. Look at your slope, you get negative K, and positive K. So it's very important that we know these. And it gives you the half-life formula. You can see that the half-life for zero order, the initial concentration is there, so that makes an impact. And for second order, the initial concentration is there. For first order, the initial concentration isn't there, which is why first order is a very constant half-life, and zero and second order half-lives are not. Okay, so something to make sure you definitely understand. Last slide of the day, I think, on the current equation sheet for you guys from the College Board, it gives you this kinetics information. Now it's not labeled, so you have to think a little bit about it, but they put it in the correct order for you. So these are your integrated rate laws, if you haven't noticed that by now. They gave you zero order integrated rate law first. They gave you first order integrated rate law. They also gave you second order integrated rate law. They also gave you the half-life for the first order. That's all they give you, so that's all you're going to need to use. Okay. Something I want to point out here is on the previous slide, it gave you all this information. What versus time gives you a linear graph? What's the slope of that graph? Like, why do I have to memorize all that? Well, you don't. If you look at your formula sheet, you know that all you have here is obviously your integrated rate law for zero order reactions here. You just have regular old concentration. So concentration versus time will give you the straight line. So don't need to memorize it. Just know on your formula sheet they're in order from zero first to second order. So concentration versus time is linear. Your slope is negative k. Easy. Look at first order. Natural log of concentration versus time is linear. Easy. Don't need to memorize it. What's your slope? Negative k. Fantastic. Look at your next one. Second order rate law. 1 over concentration versus time is linear. What's your slope? Positive k. All the answers are right here, guys. Okay, so it's just a matter of using your equation sheet, knowing what's there, and knowing what you're looking for. So again, concentration versus time, slope negative k for zero order, natural log versus time, negative k for slope for first order, and second order, 1 over concentration versus time. And again, your slope is positive k. All right, there's a bunch of practice problems in your packet that we'll do. Iodine clock reaction lab where we apply a lot of this. And there's only one short lesson left in the unit, and we'll do that at a later point in time. All right, thanks guys.